Hello everybody, this is BKC back in From the Depths. And today we're not on my engine testing platform because my engine testing platform has gotten so big and so laggy that it's pretty hard to spawn in. So what I've been doing lately is I've been cutting it up and making it smaller into smaller rafts and posting it on the workshop for you guys. And today I just want to make a little spotlight video showing the rafts and what you can expect from them. And the first raft here is called Small Cruise Engine. And the reason I did it first is because someone who was having trouble with engines was looking for an engine that was about, I think, between 500 and 700 horsepower with about a 400 power per fuel rating in a 3.5 to 4 inch density. So, and they were having trouble making motors that fit that bill. So I tried and I tried and I tried and I couldn't get those stats, mainly because they're so terrible. And I finally came up with this motor right here. It's a little bitty 4-cylinder, and it's a beam motor. It's with a pretty long beam motor, and it's got 4 carbs that share. The back one doesn't share with anything, and it's got 8 turbos and 4 superchargers. And I had to actually make it inefficient because I couldn't get those stats building any motor the way I normally build them. So what I did is I built it, and it came out a 4x5x9 which is a 180 binding box, and I put the stats on it for the density at the different power ratings, and I put the power per fuel and fuel numbers like I do on all my other engines, and I put the material cost of the motor, and it uses 13 exhaust gases, and I think that is 2.34. Let me run the motor real quick. I forgot what yeah, that's the efficiency of the turbos. It's a 2.34 efficiency that the turbos see with 13 exhaust gases, and I put signs on it showing where I made it inefficient to meet the design goals, and or how to improve it. And the first thing is to get the body box out that big, to get the density that low, I had to make it 5 wide, and I did that by bringing the exhaust out wide, and to get the efficiency down, I had to waste exhaust. So I wasted some exhaust, and I pointed out a few other places that you could make it better with little bitty signs, like removing the superchargers, because superchargers do almost anything. Replace the turbos with non-inlines, which would lower the binding box. If we took the superchargers off, we wouldn't need that space, and that would increase the body box. Wrapping the exhaust manifold down would save some space, and laying the front cylinder down and would allow us to remove 2 cranks and put the cylinder under the carb, still maintain the sharing, still maintain the benefits of the turbo, and save us a little bit in parts and material cost for having, you know, the same layout and the same everything. It would just cut a little bit of material cost off. And this engine uses 235.5 material. Now, making all the changes in the that the signs point out, you would end up with this little engine over here. As you can see, it's much smaller. Where is the binding? Oh, here it is. It's a 3x3x8 versus a 4x5x9, which is 180 versus 72 binding box. And I put the densities of the power again, where you could see how running engines at different power shows different efficiencies. And then, you know, the standard old stats that I normally put with the power, and then the increases received over the other motor. And we could see that it's across the board. It's 2.5 times smaller and 2.5 times denser, and the size of the motor is the same cylinder count, the same power, and it has this at 10% load. It uses the same amount of fuel, even though we don't have the superchargers anymore. Which is where the superchargers should make the biggest difference, but they don't do anything because this motor uses 0.3 fuel with 250 power per fuel, and this motor makes 209 power per fuel, but which is not enough to actually take that much off of the fuel usage. So the superchargers really don't do anything, and when we get up into the higher range, we go from 0.9 to 0.8, which is a 17.8% increase in efficiency, almost like having another turbo on each carburetor. And then when we go to the top end, power per fuel jumps up from 481 to 771, and fuel consumption goes from 1.5 down to 0.9, which is a 60.3% increase in efficiency. And if we look at the densities running at 10%, the density is only 0.39 power per block, and this one is 0.97, which is 2.5%. I mean 2.5 times. And then running this engine at 50% load, it gives it a density of 1.94, whereas this one running at half power is 4.86 density, which is more than what this one is running at full power. And then this one running at full power is 3.89 density, whereas this one is a 9.72 density. And if we look at the material cost, because this is a lot smaller, it takes less pipes to plumb up. It doesn't use superchargers. It doesn't use anything that is wasteful. The material cost goes from 235.5 material down to 203.25 material, which is an increase of, or a decrease of 15.8% material cost. So, and then this engine gets 21 exhaust gas because I didn't waste the extra exhaust, and the turbos get a 3.04% increase in efficiency. So if you add all the efficiencies up together, it adds up to a good bit. It adds up to a nice increase in efficiency across the board, both in material cost, fuel savings, everything. Because power-wise, they're the exact same motor. Layout-wise, they're very, very similar. But this motor is just fully optimized, and this one is not. This one is built to meet the design goals that the person wanted. So this is the first Raft, and I'll be back in a second with the next one. Okay, this is the parts learning Raft, and I got the idea from this because trying to build stuff that I haven't built in a while, like lab systems and stuff like that, sometimes I always have to go back and I can't remember how to do it, so I go back to the basic tutorials that come with the game. And I noticed that a new player following those tutorials, they're really just showing you how to connect things and what is the minimum requirement to get things working. It doesn't tell you anything useful really about the parts. So I built this Raft more as an interactive tutorial more than anything else. And what it is, the way it's laid out is each row covers one part of all the engine parts, and right here is the a Lua box you could click on, and inside is some text about the Raft, and it gives you some useful information on engines and their parts. And the first row I've done engine blocks, and at the beginning of the row I have information about the engine block, and I got examples. And on an engine block there's not really much to show other than the way things can connect. And I put signs by each pedestal explaining what it covers, just showing that a cylinder can connect to the front of an engine block, a crank can connect to the front, and an adapter can connect the same as a crank. And in the next row we have the crankshaft and a Lua box next to it showing explaining stuff about a Lua box, and examples showing that cylinders could connect to a crank on 5 sides, that adapters can connect to cranks on 5 sides, and that cranks could be extended to as long as you want. In the next row we have a Lua box explaining about adapters, and it shows that cylinders can be connected to adapters the same as cranks on all 5 sides. That is not connected to a crank or engine block or a crank. And then this shows that adapters can connect to cranks, and that orientation of the adapter doesn't matter. And this shows that only cylinders can connect to adapters, that no other part could be connected to an adapter. Adapters will not hold carburetors or anything like that, not that they would do any good. And then on the next row we talk about the cylinder in the Lua box, and we show some examples like the parts that could be connected. Turbos can be connected on their exhaust side, carburetors can be connected, injectors can be connected, and exhaust can be connected. And then here we have all the parts, which would be a hybrid engine, and it explains the cylinder info, getting information from the cylinder. And this example, it shows a little bit about how cylinders share the carburetor. And then in this row we had the injector with information about the injector. we show that how much power injectors make, and how we control the heat of an injector. That that injectors make more heat than carbureted engines. And then here we show how exhaust can remove heat from a carbureted engine, and it lets you compare between the two because they're the same exact design. And then here shows how a radiator can pull heat out the engine, and lets you compare between exhaust and a radiator. And here on this row we talk about the carburetor with information on it, and we show how the carburetors do the exact same thing as the injector, but since they make less power and use less fuel, they don't quite make as much heat, but they're not totally immune to the heat. And so you can compare between carburetor and injector here, because I have 4 carburetors on this motor making 400 power, the same as this injector motor that should make 400 power. And in this example we show the same thing, that exhaust can take heat away from the cylinder. Since I needed 2 exhausts to take away the heat, we can't get 400 horsepower, but we can only get 300 horsepower out of this cylinder. But it still shows how much more efficient carburetors run, and you can compare it to that motor over there, even though it's not a direct comparison because this was only making 300 and that was making 400. But and then this motor is the same thing as that, showing that how a radiator can be used to control the heat of a carburetor. And in this row we have the supercharger with information about superchargers, and it shows the supercharger and how it affects efficiency at different RPM. So we just got a single cylinder carbureted motor with a supercharger on it, so you can run it and compare it to see how the supercharger drops off in efficiency as you rev the RPMs. And here it shows how superchargers can share, and that they have weird attachment points. That this supercharger is connected to both of those carburetors and still connects. And here we show that adding more superchargers per carburetor does basically the same thing as turbos. Here we have 43% increase in efficiency. Here each carburetor has 43% increase in efficiency, and here we have 194% increase in efficiency. In this row we go over turbos with information on the turbo. Here we show the difference between series and parallel turbos and their efficiency, and you can compare between one supercharger here and one turbo here, and you can compare between series and parallel here, where this parallel exhaust gets 18% efficiency. Let's see, I've got 2 exhausts feeding into this one, so it should be 31% efficiency, and it lets you compare between the two. And then in this example we show that stuff is up, shows how running two exhausts in parallel stacks its bonuses the same way as carburetors do, and unless you compare between 2 turbos versus 3 superchargers. And then in this row we learn about radiators with some information in the little box about radiators. Here it shows a small radiator trying to control the heat from 2 injectors. It shows how it just keeps the heat under control of 2 injectors. And here we show that the bigger radiator keeps the motor cooler, but it uses more fuel. And here it shows connections of radiators. It shows that they could connect to cranks, it could connect to cylinders, it could connect frontwards, it could connect backwards, it could connect all kinds of weird ways, just as long as it's connected to a cylinder or a crank or another radiator. And it just gives some examples of some weird connections. And then here in this box we learned about the exhaust, and in this example we show all the weird connection points from exhaust and how they don't care about being plumbed into things that make no sense, or a dead-ended pipe is still considered closed. I have multiple pipes, and that exhaust doesn't really care about the length of the exhaust. It doesn't affect how much heat it can take away. It doesn't affect the turbos. It doesn't really affect anything. So that's what we learned here. And here it shows how much cooling one exhaust can provide. And then it shows in this example how we have a busted exhaust pipe right here. It shows how that even though I'm collecting 4, I probably should put that on the side with the that the player's on, but it shows how that running collecting your exhaust parallel and sending it to a turbo serially, you lose the boost if it gets destroyed. That opening up an exhaust loses all the boost to a turbocharger. You still get the cooling of the exhaust, and then if this was in your hull, you would get a slightly reduced amount of cooling because it wouldn't have clear flow out of the vehicle, but you would still lose your boost and your efficiency from your turbochargers. Superchargers it wouldn't affect, but turbochargers it does. So that is the Engines Learning Raft, and I'll put links in the descriptions if you want to check it out, and I'll be back in a second with the next raft. Okay, now we're back on the third raft, and I called this raft the anatomy of an engine, and it is laid out in rows, and what its purpose is to show an engine and how the math works in an engine. So to keep the math consistent, throwing 100 different motors at it would be very confusing. So what we needed is a consistent test subject, and the test subject I chose was my 3T engine, because the 3T engine is my smallest motor to keep the size down, and it uses every trick in the book to get its stats. So in this box we have information about my 3T design, and it explains about the binding box and how the 3T, how many cubes of space that the red cubes are the space that the motor uses, and pretty much the entire center of the box is used, but just the blue ones here on the outside. And I think yeah, there's one right in front of this block that is not being used, and of course if you put the engine on the ground, this block right here wouldn't be used. But it just shows that the 3T does have a lot of empty space. I wish you could see the different painted colors of the blocks through these blocks, because then it would really look cool. But this is the core of the 3T with one exhaust per cylinder per carb that the cylinder sees to keep it cool. So just the most basic exhaust you can have and keep the engine cool. And that lets you come back and compare just the core with the built engine to see how bad the fuel consumption, the heat problem is, and all that stuff. That the design of the motor, of the core, is not 100% the key to the motor. That the wrap of the superchargers and the exhaust and the turbos and all that stuff is what makes the motor, makes most of the specs of the motor. And here all I do is add the superchargers to show that they do, once again, that they do very, very, very little. And here it shows what you got to do to get a noticeable effect on the 3T core with superchargers, and which is basically just loaded out with superchargers, but it still doesn't do very much. And it lets you compare these motors back with the fully built 3T for comparison. And in this row we cover mostly turbos, series and parallel. And what I've done is I basically took a fully built 3T and I removed the superchargers, and it lets you compare between the fully built engine and the fully built engine without the turbos. I mean, without the supercharger. So you can see how little that it really does. It does have a little bit of effect on the 3T, because when you start making high power per fuel numbers, the 5% that the which is usually going to be in the upper end, the supercharger doesn't make a lot of boost in that range. But when you have high numbers, which is going to be at high loads, 5% of a high number still turns out to be a little bit. So it makes the superchargers not necessary if you don't have space above the carbs. But if you do have space above the carbs, putting them in doesn't really hurt anything, because it gives you less fuel usage and higher power per fuel numbers without hurting density of the motor. And it lets you compare just between the two without the supercharger. Here I had the 3T built out with a full exhaust arrangement, but instead of running the turbos in series, I put the same amount of turbos on in parallel, and it lets you compare between series and parallel exhaust and see how bad parallel exhaust is. And then here I have just two turbos, one per carburetor, and it shows how much better just having series exhaust is over a parallel exhaust. That one series turbocharger is better than 3 parallel turbochargers. and it lets you compare between them. And if you want to, you can compare between one turbo in series versus one supercharger on the basic core. If you wanted to, you have a little bit more heat on the core because it doesn't have a full exhaust package, but it still lets you compare. And then here we have two turbos on the core, and lets you compare between 1 and 2. And if you want to compare between 3, you could come back to here, and lets you check out the efficiency range with the amount of exhaust being fed from the 3T. And here on this one we have one supercharger with just 1 and 2 turbos. So we've added the supercharger back in with just one turbo, so you can compare between one turbo with a supercharger and without, or you could compare between 3 superchargers and three turbos and one supercharger versus 1 turbo and 2 turbos with the supercharger versus the fully built motor. And then I have a exploded view of the 3T, showing the pieces, how simple it is, and the pieces how they connect, and just lets you get really inside the motor and kind of look at it a little bit better. If I took a little more time, I could have used mimic blocks and scaled some of the parts up bigger and smaller, but I think this is good. Using the actual parts is good enough. And this is the anatomy of an engine, and most of the information in this is interactive, where you could go and compare between the engines. And most of the math and the information for all the formulas is in the Lua box, right here in one box. So you could spend a good hour, reading here and going back and forth, reading up about something, then go and check it out, and then coming back and reading a little bit more, and then going back and check the engines. And that's pretty much it for the anatomy of an engine, Raft. And I'll be back in a second with the last one that I have built so far. Okay, now we're back on the last Raft, and the last Raft is small engines. And what it is my collection of small engines from my engine testing Raft, and it is set out. It's laid out in rows, and the engines are pretty much laid out by their binding box size. Not always, but for the most part. If two engines need to be next to each other for comparison for a point that I'm trying to make, they won't be laid out by binding box. They'll be laid out next to each other so you can see. And it's laid out in rows in a serpentine pattern. You just start at the big arrow and you just walk the Raft in the serpentine pattern. I put blocks in the way so you could just walk around it in a serpentine pattern. And by each engine I have a Lua box explaining, giving information and a little bit of lesson, a little bit of design theory, or important features about that particular motor. And I have signs explaining, giving all the stats that I would have on my engine testing Raft. So you don't have to go into the Lua box just to compare. You could go into Lua box, read about the motor, then come out and play around with the engine and compare it. And I have signs between motors explaining what you should be comparing between two different motors. And here we have our basic parallel turbos and the stats of it. And here we have the same core layout, but with parallel collection series turbos, and it lets you compare between the two. And in this box, it explains why series collection and parallel exhaust is better, and it shows that parallel exhaust collection, or the exhaust manifold, is done in red, and that the series section is done in blue. And in this motor we have a very compact little motor that uses a series 4 series turbos. It makes 200 horsepower. It's not really efficient, but it's very compact, and it shares the same binding box of the first motor, but makes twice the power. So the density is up on it, but the efficiency really doesn't go that much further compared to the parallel exhaust, the parallel turbos. Back when the material cost was a lot higher, this motor was pretty much favored because of the material cost was so low for the power per fuel that it made, that it was best to use this motor over building bigger motors. But now that the resource points have dropped for all parts, that's not the case anymore. But and it explains the problem with this motor, that the compactness of the turbo layout blocks the exhaust, so you can't get a lot of exhaust to the series side, so it hurts the efficiency, even though the density is higher. On this motor, the efficiency suffers. And this motor shows how we fixed that problem and expose more exhaust, and a little bit about part sharing, because we're sharing a carburetor, and shows that sharing a carburetor can increase the power versus having two carburetors per cylinder. One carburetor per cylinder on a 2-cylinder. We can have the same amount of power with one carburetor, which helps increase density, even though the density of this motor is not higher than this motor. Because of exposing more exhaust and actually using more exhaust, the binding box gets bigger, but the efficiency goes way up. And in this little motor, I show about as high as you could push the density on a single cylinder or a small motor. And this is the smallest motor out of this whole row. Well, the smallest motor on the whole Raft, really, until we start getting to Injector Motors. And it kind of beats pretty much all of them in, except for this one, in power per fuel. And it has the highest density out of all these motors at 7.41 density, and it's a very simple to build little motor. The problem with it is it doesn't have any kind of sharing, because there's nothing to share with. It's just a single cylinder, but it gives fairly decent efficiency, pushing close to almost 200 power per fuel in a 3x3 package is pretty good. So this is a new motor that I don't even have on my engine testing Raft yet. It's just when I was laying this out, I had a good idea for a motor, and I said, wow, I think I found a way to make the most compact motor ever. And so this is a new little motor that's only on this Raft, and it also is a good example for showing chaining motors and how chaining motors works, which we have right here. and it lets you compare between a chained motor and a non-chained motor, and it shows you how to chain motors, or how I chain motors. Some builders spend excessive amount of time making a repeatable pattern motor, where you could just copy a slice of a motor and just keep pasting it over and over and over. I kind of feel that's a huge waste of time. Knowing how to build motors and knowing how to chain motors together is a better way of going about it, because if you look on a lot of the other engine raft out there, there's a lot of massively huge engines that nobody ever uses, because they're so massive, because they're set up to be repeatable pattern motors, where they indicate like the start of the motor with a black box, and then they'll show like a a white stick showing a repeatable pattern section, and then they'll show another black box showing the end of the motors. So what you would do is you would copy the start section and then copy the middle section, and just keep repeating the middle section over and over and over out to the power that you want it, and then copy the end section, and then put it on. And it's a good thing to do, but I don't do it, because I think it's just a waste of time. It makes motors bigger. It makes the middle section of the core bigger, because you have to plumb it up to where exhaust pipes are in a specific spot, to where when you connect it to the next section, it meets up and chains the exhaust properly. So I don't do that. So this little motor shows you how to chain exhaust properly, or chain motors fairly easy. And what you do is just copy and paste this motor, or prefab this motor, and paste one in front of the other. And all you got to do is flip this exhaust around, which would be the exhaust, the turbo in red. You'd flip it around, which would be this one. So it'd be facing the other way, but by flipping it around, it changes the serial side of this engine to the serial side of this engine. And removing this pipe shown in yellow, I left it there so you can see its location, was plumbing in the parallel side of this motor into the serial side, which is no longer connected, is connected to the serial side of this motor. So the exhaust comes in here, goes around this motor, then comes into this, and then goes around this motor. So it's all in series. And then so the only thing left is to change the pipe shown in green from a through pipe to a corner pipe, to detach it from the serial side, and change the corner pipes here and here shown in purple to elbow pipes, because they would be just elbows. They would just be corner pipes, and so we change them to what they're called L junctions. I call them elbows. Oops, I'm stuck. And then connect the parallel connection side, or the exhaust manifold, with the pipe showed in white, which kind of comes out, looks like silver. A little trick: paint your exhaust pipes white if you want them to look like they're chrome. Okay, I had to get unstuck. And this is my 3T. If you download Anatomy of the Engine Raft, you don't really need any information or anything about the 3T, because it's all covered in the Anatomy of an Engine Raft. But I do have a little bit more insight on the 3T in this raft, to separate it just a little bit. And then this is the 3W motor, and it explains about the 3T and how the 3W is the 3T engine. In essence, it is just a modification of the 3T, and I call it the 3W because I took the T configuration of the 3T and I turned the cylinders upright to make them vertical, which is, you know, if you looked at it, 3 cylinders, you know, side by side. If I could angle them any, I would angle them out in a W pattern, or you could flip the motor upside down. It'd be the 3M, but due to copyright restrictions, I don't want to use that name. So, but it shows how I took the 3T, which is one of my earlier designs that I've got this efficient, but it lacks power in that it uses a lot of space, or has a lot of wasted space, and I tried to bring the density up by not wasting as much space. To bring the density up in the same space, you have to use more of the space with power parts. And so it in this box it explains what I did to the 3T to make it the 3W, which is turn the cylinders upright to more efficiently collect more exhaust to get the parts count down, but mostly for the efficient exhaust collection. In here, each cylinder makes 2 exhausts per port, and by putting the cylinders vertically with one little 4-way pipe here, I'm able to collect 6 exhausts. With another 4-way and 3 through pipes, I'm able to collect another 6 exhausts, and then with 2 more corner pipes, two more corner pipes here, and 2 more corner pipes here, I'm able to collect 6 more exhaust. To get the to make more power, what I had to do is I had to move things around to get the empty space more centralized on the back of the motor. And to do that, what we had to do is flip the serial turbo flow of the turbos. None of the turbos, the superchargers, the carbs, or anything moved. Even the cylinders didn't move. So that's why I consider the 3W still the 3T, even though it's massively different. All it really did was I reversed the flow of the turbos to better facilitate the new turbos. So you can see it's flipped upside down, the exhaust pattern from the 3T, and to get more turbos on and more carburetors and a supercharger on, we had to and rotate the which we didn't move the cylinders. They're still in the 3 pattern. In the T pattern, but since they don't connect, they don't look like a T anymore. We just rotated them. They didn't move, we just rotated them. And to do that, to do all these combinations, what we had to do is lower the crank and put an adapter on each side. What that did is it got the engine block out from between the 2 carbs that we're going to add, and adding those carbs causes us to lose 1 exhaust out the rear cylinders, but adding the carburetor, like I said, loses us 1 exhaust, but then it adds 3 more exhausts by having two carbs. So and then that centralizes all the space in the rear, so we could put the two more turbos per carb. It would ideally be better and more efficient with 3 turbos per carb, but that would break the binding box, and I wanted to keep it the same size as the 3T. But with lowering the crank, it lets us get the supercharger in here that shares between the two carburetors, and moving the connection point on where the parallel and the serial side of the exhaust meet from here to back here lets the chain go from to this turbo for this turbo down here around through all of these and back to this and come out and exit the engine without breaking the binding box. So that is the 3W, and it's a pretty good little motor, but it's still not maximized. It was the evolution of the 3T, but it still can be improved further. And this is the 3W with, well, it's more of it wouldn't be a W, because what we did in this motor, I really don't know what to call this motor. What we did is we took the 3W and we flipped it 180 degrees, and the reason we did that is if you look at the 3W, that there's a massive amount of empty space in the front. So if we put the engine block up here, we can use some of that space and free up another spot. And what we would use that spot for, which now is in the front, is if we put the engine block in the back, we could extend the crank out and get another cylinder in here. And getting another cylinder in there gives us another 200 horsepower because it shares between the carbs, but we lose the supercharger, which hurts efficiency just a little bit. And you can see that going from a 3T, we get 1250 power per fuel. Going to the 3W, we still keep 1175, which is still good, and fuel usage goes up, but not that much. In the 800 horsepower version, we keep the same size, but fuel economy goes down a little bit. I mean, the power per fuel number goes down a little bit, and the efficiency, I mean, the actual fuel usage goes up a little bit, and we're borderlining on the point where I don't, really consider it as efficient as much, because this would still have a C efficiency rating. This would still maintain I think this would be a D efficiency rating, and I think this would just make a D, but it's starting to get close to an E efficiency rating. But it just shows that motors can be manipulated, and it shows you how to manipulate them a little bit. And this motor, I show that it's real easy to chain to itself, another motor to itself. All you would have to do is, if you flipped another motor 180 degrees to itself and mounted them front to front and left one space, because this motor could be made a little bit more efficient by collecting this wasted exhaust in here, but that breaks the binding box. And if we were gonna collect this extra 2 exhaust here and break the binding box, you'd be better off, I mean, if you just needed 800 horsepower and you had the room, like say your craft was using the space at the bottom or the space right here, but didn't use the space in front of this cylinder, then you could just collect that exhaust and make it a little bit more efficient. But if you wanted more power and you wanted to use this design, you could chain it to itself and make it more efficient fairly easy by putting another one put them face to face, and space them out by 1. And by spacing them out by 1 for one reason, it would hurt the density a little bit, because the density of this motor is 10.67, and you can see that the 3T has a density of 533, and this one has a density of 80, and this one has a density of 10.67. So adding more cylinders in the same space increases the density, but chaining them two together would increase the efficiency even more. Usually carrying the same density if you can butt them up without wasting any space, or adding any additional parts, or going outside the binding box to chain them together. In this motor, you would lose a little bit of space, because if I butted another one up against this motor, the exhaust would have to be right here out of this turbo, and there's no way to do that without wasting. You're pretty much trapped. So you probably could sit it down and figure it out, but the best way to do it would be mount them front to front without leaving one space to between them. And the reason we would do that is we could come in the back of the motor and remove the engine block, because we would want to share some core parts between the two motors, and to do that you would have to be on the same crank. So you would extend the crank out two cranks, because it would have to make up for the space between the motors, and it would have to make up for the space of the block that we took. Well, no, we would have the crank right here. We would only have to make one extra crank for the to make up for the space that the motors are spaced, and we would just have that empty space in the front of the motor. And to link them together, like I said, we would want to collect this exhaust. So you'd put a through pipe in there facing up. You'd put a through pipe here and here on the other motor, and a through pipe connecting down to make use of the front exhaust on both motors, which would feed more exhaust to our turbos. It'd feed 4 more exhaust to the turbos, and then you'd have 2 carburetors right next to each other. So you would want to put a supercharger in there to boost efficiency a little bit more. It would give you additional 5% across the board, and to link them together, the purple pipe would be replaced with a through pipe on both the motors, which would connect the parallel sides together. And the serial sides, all you'd have to do on one of the motor, replace the red turbo around to disconnect it from the parallel side, and connect it serially in with the other side. And the white pipe you would add in to connect the two the parallel turbo chain together. And the exhaust would be out right here, because we would have the empty space for the exhaust to exit out in the middle of the engine. So this engine, not quite as clean to chain them together, but it can be done. And that just kind of shows how designs can be manipulated, because the 3T fits in a 3x3, I mean a 3x5x5 box, and all of these motors fit in a 3x3x5 box. So that just shows how I got a mistake on this one. I didn't notice, but it's already on the workshop with one little mistake. It won't kill anybody. But it just shows a little bit how you can manipulate motors and in the same bind box, and gives you a little bit of insight on, you know, how through the years I've built motors and learned to manipulate them. And this motor just made the cutoff of the 100 binding box from you know, the arbitrary limit I put on 100 binding box, but it's really a mid-size motor tuned for power, and it just so happens that a 5x5x4 binding box that this uses is exactly 100, and so it included on the Raft. And what makes this motor special is this was the first motor that I efficiently made, you know, 3,055 power per fuel. You know, in this size motor, and it's the first one that I did it, so I kept it, and it's a pretty clean looking motor. The only thing bothers me is how I have to collect the parallel side. The engine block gets in the way, so it kind of gets a little ugly, but it still uses, you know, it still doesn't go outside the 4x5x5 binding box. And this motor would be super easy to chain to another motor, because the inlet, the parallel side is right here, where it feeds into the serial side is right here, and the exhaust is right here. So putting this motor front to front would be super easy to connect them all together and chain them all, and the efficiency would go up even higher. I think 3 turbos max efficiency per carb is 5,066, and it would reach that if you put 2 of those together. The next motor is a unique little motor that I built when I was experimenting with odd binding box sizes. I mean even binding box sizes, so a 4x4x4 cube. And this is a 600 horsepower little cube motor, and it maintains pretty decent efficiency, and it explains why I came about it, what I had to do on this motor. And then it's got my one of my first motors that I got to, or not the first motor I got to this high of efficiency, but the one of the experimental motors that I made to test turbos versus, you know, sharing versus all that stuff. And so it's on here as a kind of like a trophy, and explains, you know, some of the stuff about it and what's the downfalls. Now this motor, if you include that it's a 4x4x7, it wouldn't fit on this Raft, but technically it's a 4x4x6 because I don't include the exhaust. And if you had a space that was 6 wide, you could put a hull pipe in to make it, you know, exit the craft. So that was a mistake that I originally had on it. I think it was a 105 binding box, because I was calling it a 7 because I was counting this pipe as being included in the motor, but that's actually the exhaust. So it's actually a 4x4x6. So that's that motor. And this motor is a kind of a spin-off of this motor, trying to fix some of its problems and get it a little bit more efficiency now that we don't have to worry about material cost. And it gets fairly efficient, but you know, by wrapping the turbos the same way as that motor, but being able to get 3 of them per carb, and a supercharger on each car. Well, it's really got 4 turbos and a supercharger on each cylinder, so you can get 200 horsepower out of it at a fairly decent efficiency. But it has a really weird use case. The density's not that big, and on a craft that would only use 200 horsepower, need 200 horsepower, and big enough to fit this motor, you kind of get into a weird scenario where other motors start making sense. So it has a weird use case, but it's a motor that I built that is kind of cool. I kind of call it the coffee table because it kind of looks like a coffee table with some stuff on it. And this motor right here is an improvement on that motor, just a complete redesign to get more power out of it, more efficiency, more everything out of it. And I came up with this motor, and it is a 400 horsepower with almost twice the density because it makes twice the power, but it reaches a really efficient point for a 400 horsepower motor. And what I did was I added 2 carbs to get 4 turbos per carb and pack it tightly in a small space. This is a 3x4x6. This is a 3x5x6. So giving up a little bit of room, you gain more density because of more power, and you get way more efficiency. So that's this little motor, and this is probably one of, I suspect, that a motor that if you need 400 horsepower on a small craft, this is probably a good way to go. If you needed a little bit, if you didn't have as much space, there is plenty of engines on this craft that have a higher density, so, with 400 horsepower. So that's that little motor. And then this is the Evil brick. I don't remember who designed it, but it's been around for a while. And basically, it's a hypercube with 1 layer cut off to cut it down to 1200 horsepower from 2400 horsepower and keep pretty much the same efficiency. And I included it on my Raft, so you know, because it's on other Rafts, but it's surrounded by a lot of useless motors, and so I just wanted to share it on my Raft and to keep it from getting lost, because it is a very good little motor, probably the pinnacle of small motor design. And then in the front row we have the Injector Motors, which I usually don't spend a lot of time designing because they I really just don't like fuel inefficient motors. But I sat down and played with them a little bit, and I came out with a new rating system that lets me see the difference between injector motors more clearly, because if you use the rating system that I've set up before, you just get really low power per fuel numbers between like 80, I think it's like 80 something to 100 and something, or I think it goes down to 60 something power per fuel, and it goes up to, at the lower RPMs, a little bit over 100 and something. But I came up with a new rating system, and the new rating system, what we do, since heat affects the power of the cylinders, we use the actual heat ratings. So we have to spend a little more time testing to get these numbers, but we use the actual power the engine makes. And this box explains the new rating system that we use the actual heat, instead of the theoretical. So this would be theoretically a 3200 horsepower motor, but it actually runs at 2898. And instead of using power per fuel, which is pretty meaningless on an injector motor because we can't do anything to affect the fuel usage of the motor, since we have no control over it, there's no point putting power per fuel numbers. So what I do is I put the binding box and I put the actual power of the motor, and then I run the motor at 10%, 50%, and 100%, and we note the actual power it makes: 320, 1598, and 2898, and we put the fuel usage that it uses at that RPMs, and then we calculate out the density at those RPMs or load levels, and we can see that this motor makes 320 power, which is 10% of the theoretical power, and uses 3 fuel with a density of 7.11 because heat hasn't affected the motor yet, which shows up in the 40 power per cylinder rating. And at 50% it makes 1598 using 17.8 fuel with a density of 35.51 and makes 199.75 power per cylinder. So it should be making 200. So it shows that 0.25 power per cylinder is lost. And at 100% it makes 298 power using 42.7 fuel with a density of 64.40, making 262.25 power per cylinder. So it shows that heat is starting to take more effect the more we rev the motor, and we're losing about 36.75 power per cylinder. Every cylinder loses that. So this is the most efficient layout I've found for injector motors, and it really doesn't use radiators. It uses exhaust to cool, and it just has a radiator here because it doesn't break the binding box. And then this is the same motor with a large radiator added to see if adding a radiator to keep the engine cooler could get some of the power back that this doesn't, that this loses, and increase the density, because this 3200 theoretical engine is losing almost 302 power due to heat. So I made this motor to test that out, and it gets a little bit more power, but not much. I think it saves 100 and something power, and to get the extra power, I mean, to save that extra power, we have to break the binding box. So the easiest way to break the binding box is the smallest side, because we want to add it. We want to add as little to the binding box as possible. So we extend the crank out to add it on, and the density plummets from 64.4 down to 55.63. So you can see here that adding a radiator not only hurts the density, it also increases the fuel usage, because we go from 3 to 3, which is nothing. We go 17.8 to 18.1, and then we go from 42.7 to 43.5. So it's not a huge increase in fuel usage, but it is a not a huge increase, but a decent little increase over the power per cylinder at full power, because this one is 62.25. This one is 375.5 power for every cylinder. So the increase from here to here is 9 power per cylinder, which is a pretty good increase because we have 8 cylinders. So it's a fairly good increase, but it's just not really worth it. And then last but not least, we have the what I call my little Bumblebee Motors for little small jets. It can be used in small boats too, but the best use case scenario is for jets, little bitty tiny jets. And we have the little 385 horsepower 3x3x3 motor, and it shows that the density on small motors can be pretty high, especially with injectors, and that we get the highest power per cylinder out of this little motor, I think, than any other motor on the any injector motor out of all of them. This one gets the highest power per cylinder, and it shows some little, I guess I would call it, some people would call them kind of cheaty, but all that's doing is manipulating the my rating system here. Since I don't include the exhaust on a cylinder, on a exiting the craft, I consider that part of the craft. We can raise the density significantly by not putting an exhaust on the motor. And what I mean by not putting an exhaust on the motor is, if this was in a jet and we only had a single sliver, just one block between the top half of the fuselage and the bottom half of the fuselage, we can shift that load from the binding box of the engine to the fuselage of the jet by using hull through pipes. And hull through pipes have a 300, I think a 300 health, whereas a iron block has 350 health, and a aluminum block, which is probably what a small jet would be made out of anyway, is 260. So exiting the craft here is not counting against the density, but is shifting the exhaust over to the hull or fuselage, and makes the binding box a 1x3x5. And this motor makes 704 power in a 1x3x5, which brings the density way up. And the last little motor I got is a 3-cylinder version of this. How I would make it, shifting the top and the bottom out of a jet with hull pipes. And I had to pipe it up here to get it to out and away from the deck, because the down-facing cylinders affects our testing. It affects the heat a little tiny bit, and it makes the block report no clear flow out of the vehicle. So in a jet that wouldn't be a problem, because it would be in the air. You'd have 3 exhausts facing down, 3 exhausts facing up through the hull, and this little motor makes an impressive 1,056 horsepower using 15.8 fuel at a density of 117.33. So this is the densest motor I've ever made. It is using a cheaty little trick to shift the exhaust over to the fuselage, but not putting any exhaust on it would make it not work. So I had to put the hull pipes on to make it, but technically its density is 117.33. So this is a cool little motor, and I hope I'll be putting the link in the description for these rafts in the description. And if you download them and like them and use them and learn something, or use one of my motors in your craft, these take a lot of time to make. Please Give me a share, a like on Steam and on YouTube, and I'll see you guys in the next one.